In this video, we're going to go over some practice problems from Chapter 7 from our textbook. Now, in Chapter 7, we're looking at roots, radicals, and root functions. But starting with Section 7.1 here, we're going to look at radical expressions and their graphs. So for the first three examples here, we want to find each root. So for this first one, we want to find the third root of negative 64. Well, this is just going to give us -4. Now, the reason being is because if we were to take -4 raised to this third power here, that would give us that -64. Okay, so that'll be our answer for that first one. For the second one here, notice we have this negative on the outside. So that negative is going to stay there on the outside, and then we want to evaluate the fourth root of 16. Well, the fourth root of 16 is going to give us 2. And this is because if we take 2 and raise it to the fourth power, we'll get that 16 there. Okay? And then we just have to keep this negative on the outside because our expression had this negative on the outside of this radical. So this would be our final answer. Now for 36 here, we want to take the square root of 100 divided by 9. Now in this case, this radical here is going to apply to the top and bottom. So we're taking the square root of 100 and the square root of 9. Now this is going to give us 10 over 3. And this is because if we were to take 10 over 3 raised to the second power here, since if we just have a square root with no number here, it's assumed to be the square root. So if we were to take 10 over 3 squared, this would give us that 100 over 9. So our final answer here is going to be 10 thirds. All right, so for the next two problems here, we want to graph the following root functions and give the domain and range for each one. So we'll start with that. Let's find the domain and range for 51 here. Now remember, the domain is going to be all of our possible values that we can plug into this function, and the range is going to be all of our possible output values. Now remember, we can never take the square root of a negative number. So this tells me the smallest value that I can plug into this x here is going to be 0. We can take the square root of 0. So our domain is going to be from 0 all the way up to infinity, as long as this number is not negative. In other words, the domain is going to be all real numbers such that x is greater than or equal to 0. And in interval notation, that's going to look like this here. We're going to have a bracket at 0 since we're including that value all the way up to infinity, and then close it with a parenthesis. So this means our smallest possible value that we can plug into this function would be 0. So with that being said, we want to figure out what our range is going to be. If the smallest possible value that's going to be plugged into here is 0, this means the smallest possible output value for this function would then be -2. So our range is going to be from -2 up to infinity. And again, we're going to have this bracket here to include this value. All right, so that's our domain and range for this function. Now we want to actually graph it. And we can do so by creating a table. We're going to plug in some values into our function and see what we get out. So we know that if we were to plug in 0 into this function, our output is going to be -2. Let's pick another nice number. We can plug in 1 into this function. We know that the square root of 1 is 1. We'll subtract 2 from that. Our output would be -1. Let's pick another nice number here. If we were to plug in, let's say 4 into this function, we know that the square root of 4 is going to give us 2. We'll subtract 2, and that'll give us 0. So these are enough points here to kind of give us an idea of what this function looks like. We're going to go ahead and plot them. So this first one is 0, comma -2, so we're going to have a point here. The next one is 1, comma -1, so we'll have a point here. And lastly, we have 4, comma 0. So this is what our function is going to look like. And it's going to go on forever in that direction. Now notice our graph matches up with the domain and range that we found here. So our domain is going to be from 0 to infinity. We can never plug in any negative values into this function. That's why we're not in either of these quadrants here. And then our possible output values is going to be from -2 all the way up to infinity. All right, let's do the same thing for our next one here. In this case, we're looking at a third root function. So we have the third root of x plus 1. We're going to do the same thing. Let's find the domain and range. Now notice in this case, we can't take the third root of a negative number, so that's not going to affect our domain. So in this case, actually, we can plug in any value into our function, and we're never going to end up taking the square root of a negative since we have this third root here. So our domain is actually going to be all real numbers. So that's going to be from -infinity up to infinity. Now, due to this, our range is also going to be all real numbers. Since we're plugging in all real numbers into our function, what's going to be outputted is also going to be all real numbers. So our range is going to be from negative infinity to infinity. Okay? And we should see that when we go ahead and graph this function. So we'll go ahead and do that. Again, we're going to create a table here, plug in some values, and see what we get out. Now, since we do have the third root here, it is in our best interest to pick nice numbers that we can plug into this function so we can get nice numbers outputted, just like we did in this first one here. So the first number that I'm going to plug in then, let's plug in a -9. If I plug -9 into this function here, I'm going to take -9 plus 1, and that's going to give me a -8. The third root of -8 is -2. So I plug in -9, I get out a nice number, -2. Another nice number that we could plug in would be -2. If I plug in -2 here and then add 1, I'm going to end up with the third root of -1, which is -1. All right, let's plug in another nice number here. If I plug in -1 into this x, I'm going to get -1 plus 1. That's going to be the third root of 0, which is just going to give me 0. Similarly, let's plug in a 0 into this x. The third root of 1 is going to be 1. And let's pick one more number. Let's pick a nice positive number. If I were to plug in 7 into this guy and add 1 to it, I'm going to get the third root of 8, which is going to give me 2. So now we'll go ahead and plot these points. If I plug in -9, I'm going to get a -2. -2 gives me a -1. -1 is 0 here. 0 is 1. And 7 is 2. So our function is going to look something like this, and this is the exact shape of a third root function here. It is just shifted 1 unit to the left. Normally a third root function would be centered at the origin here. And similarly for a square root function, this guy is shifted 2 units down. Usually it would be at this origin and go this direction. So these are our two functions here. All right, so for the next two examples here, we're going to use the following rules for evaluating nth roots of nth powers. Now, this can be found directly in our textbook, but if we have that n as an even number, and we're trying to take the nth root of some number a raised to that nth power, this can be simplified to just the absolute value of that number a. Now, on the other hand, if n is going to be an odd number, and we want to evaluate the same thing here, this is going to be simplified just to that number a. Okay? Now this is only the case if we have the same index for our root and the same power under our radical. So let's look at this first example here for 59. We're taking the square root of -10 squared. So our square root and this power here under that root are the same. So what we can do is use our first rule here, since both of these are going to be even. So this is just going to be simplified to the absolute value of -10, which gives us +10. Right? And that's it for that one. For 63, we're going to use the second rule here. Since n is odd, we have all right, so for the last two examples in this section, we're going to use the following rules for evaluating nth powers of nth roots. Now, these can be found directly in our textbook, but if we have that n as an even number and we're trying to evaluate the nth power of a raised to the nth power, the nth root of a raised to the nth power, where a is going to be any real number, then this can just be simplified to the absolute value of that number a. On the other hand, if n is going to be an odd number, and we want to evaluate the same thing, this is just going to be that value of a under our radical. So let's apply these rules to these two questions here. In 59, we're taking the square root of -10 squared. So this n here is going to be an even number. So this means that this is just going to be simplified to the absolute value of that number under our root, which is -10. And we know that the absolute value of -10 gives us +10. All right, now on the other hand, for question 63 here, notice we're taking the fifth root of -9 raised to the fifth power. So this n here is odd, so we're going to use this second rule. This entire thing here is just going to simplify to whatever that number is under our radical. In this case, it's going to be -9. So this entire thing is going to simplify to -9. All right, so this brings us to section 7.2, where we're going to be looking at rational exponents. Now, in this section, we're going to be using a lot of the same rules that we saw in previous sections when dealing with exponential expressions, but now we're dealing with rational exponents. So these are going to introduce radicals. So for this first one here, we have -27 raised to the 1/3 power. Well, this rational exponent here can be rewritten as a radical by taking the third root of -27. Now, to evaluate this, this is just going to give us a -3. And this is because -3 cubed gives us that -27. Okay, so that's it for that one. That is our final answer. For 36 here, we have 81 raised to the -3/2. Now, just like we've seen in previous sections, we don't want to deal with the negative exponents. So before we do anything further, what we're going to do is rewrite this as an expression with positive exponents. So we know how to do that. We're going to rewrite this as 1 over this exponential expression, now with a positive exponent. So we've seen this before in previous sections. Now, what we're going to do that's new to this section here is we're going to rewrite this exponential expression using some of our exponent rules. In this case, since 81 is a perfect square, this tells me that maybe I should take the square root of this first and then cube it. So I'm going to rewrite this 3/2 as we're going to have 81 raised to the half power and then cubing that. Our exponent rules tell us that if we were to cube this entire thing, this is the same thing as raising this number to the 3/2 power. So we're just pulling that cube out for now so that we can evaluate this and then cube it. Okay, evaluating this, we have 81 raised to the 1/2 power. This is going to be the same thing as the square root of 81, and then we're cubing it. So this is going to give us 1 over 9 cubed, which is going to give us 1 over 729. So this would be our final answer there. All right, let's look at this next one here. For 39, we again have a negative exponent. Now, in this case, since we have a fraction, when we rewrite this with positive exponents, what we're going to do is just flip the numerator and the denominator. So this is going to become 81 over 16 raised to the positive 3/4 power. All right, now we're going to use the same rule that we saw with 36 here. Let's rewrite this rational exponent so that we can evaluate one thing at a time. 81 and 16 look like they might be perfect fours or fourth roots, so we can take the fourth root of this. So what I'm going to do is rewrite this as we're going to have 81 over 16 raised to the 1/4 power, and then I'm going to cube that. Okay? So our exponent rules tell us that if we wanted to evaluate this, if we take something raised to the 1/4 power and then cube that, that's going to be the same thing as that entire thing raised to the 3/4 power due to one of our exponent power rules. So like I said, 81 and 16 look like nice numbers. It looks like we might be able to take this to the 1/4 power or take the fourth root of them. So let's go ahead and try that and then cube it. So this is going to be the same thing as the fourth root of 81 over 16. Now the fourth root of 81 is going to give us 3. This is because if I take 3 to the fourth power, that gives me 81. And then 16 raised to the 1/4 power is the same thing as taking the fourth root of 16. That's going to give me 2. Since if I take 2 raised to the fourth power, that'll give me 16. And then we still have this cube on the outside. So what we're going to do is cube both of these. That's another exponent rule that we saw. This cube is going to apply to the numerator and the denominator. So this is going to give us 27 over 8 as our final answer. And again, I just want to emphasize that we got these values because 3 raised to the fourth power gives us 81, and 2 raised to the fourth power gives us 16. Okay, so by taking these to the 1/4 power, we got these values. All right, now for the next several questions here, we're given two exponential expressions, and we want to write each of these exponents as a radical. So rewriting these guys in our radical form. So looking at this first one here, notice we have 5 times x raised to the 2/3 power. So this is going to be the same thing as 5 times x raised to the 2/3 power. So this exponent is only being applied to this variable x here. So we want to rewrite this in as a radical. I'm going to have this 5 on the outside. Then I'm going to have my radical and my x underneath. Now, the nth root of my radical is going to be given by the denominator in my exponent here. So this is going to be the third root of x, and this entire thing is going to be raised to the second power. Let's scoot that over. There we go. So that would be this guy written as a radical expression. Let's look at this next one here. I have z raised to the negative 4 over 9. Okay, so what we're going to do is rewrite this as a radical, but notice we have a negative exponent here. So before we do anything, we want to first write this with the positive exponents. We can do so by writing this as 1 over z raised to the 4 over 9 power. All right, so now we can rewrite this as a radical expression. Again, our root is going to be given by the denominator. So this is going to be the ninth root of z raised to the fourth power. So this would be our final answer, this exponential expression written as a radical. Now, on the other hand, the next several examples, what we want to do is go in the opposite direction. We want to write each radical as an exponent and then simplify it. So let's look at this first one here. We're taking the square root of 2 raised to the 12th power. Well, let's rewrite this as an exponent first. So this is going to be 2 raised to the 12th power, and we're raising this to the 1/2 power, since taking the square root is the same thing as raising something to the 1/2 power. Mm. Now, let's use our exponent rules to simplify. This is going to be the same thing as 2 raised to the 12 divided by 2. So we're going to have 2 raised to the 12 divided by 2, which is going to be the same thing as 2 raised to the 6th power, which is the same thing as 64. Okay. So this entire radical expression here simplifies to be 64. Let's do the same thing for this next problem. We're taking the third root of 4 raised to the ninth power. So the first thing that we want to do is rewrite this as an exponential. So this is going to be 4 raised to the 9 thirds power. Since we're taking the third root, that's going to be the guy in our denominator. So we'll keep simplifying this. This is going to be 4 raised to the 9 divided by 3, which is the third power. And 4 cubed is also going to give us 64. All right, and in the last two examples in this section, we want to simplify each of these expressions. So we're going to be using our exponent rules, but again, our exponents are going to be rational. So for 67 here, we have y raised to the 7/3 power times raised to the negative 4/3 power. Well, we know that if we're going to multiply two exponential expressions that have the same base, all we have to do is add their exponents together. So this is going to be the same thing as y raised to the 7/3 power plus negative 4/3. Okay, these guys have the same denominator, so we can just go ahead and add them together. This is going to be y raised to the 7 minus 4 over 3. So this is y raised to the 3/3 power, which just gives us y. So this entire thing simplifies to y. All right, let's look at this next one here. Now, in this case, we have two different bases. We have an r and an s here, so we have to be careful with that. But notice in our numerator here, we have this entire thing raised to the 15th power. Well, our exponent rules tell us that this 15 is going to apply to this expression and this guy. So let's go ahead and rewrite it this way first. We're going to have r raised to the 1/5 times 15, s raised to the 2/3 times 15. Those are all our exponents, all over r squared. So let's go ahead and simplify this. We're going to end up with r raised to the 15 divided by 5 here. So that's going to be r. Actually, I'll just go ahead and rewrite that. And then s raised to the 30 divided by 3, all over r squared. So let's keep simplifying. R raised to the 15 divided by 5 is going to be r cubed. Then we have s raised to the 30 divided by 3. So this is going to be s raised to the 10th power, all over r squared. Okay, so we simplified the numerator. Now we need to simplify this entire thing. Well, we're going to look at our quotient rule here. It's similar to our power rule that we saw in this first example. But if we're going to be dividing two exponential expressions that have the same base, what we can do is subtract their exponents. So this is going to be the same thing as r raised to the 3 minus 2. And then we still have this s guy here. They have different bases, so we can't combine the s with the r. This is going to be r raised to the first power times s raised to the 10th power. And that's as far as we can simplify it. So those are all of our problems for section 7.2. I just want to emphasize that there were a lot of new exponential rules introduced when we're looking at rational exponents and how they relate to radical expressions. So if you were lost on any of these, especially converting from exponent to radical and vice versa, make sure that you are checking out the textbook first because it does list all of these rules very nicely there. All right, so this brings us to our last section in this video. In section 7.3, we're going to be looking at simplifying radical expressions using the distance formula, so finding the distance between 2 points and graphing a circle. So let's start with these four examples here. We want to perform the indicated operations and simplify if possible. So let's get this first one. For 26 here, we're taking the product of two fourth roots here. So what we're going to use in in this case is the product rule. And it says the product of two nth roots is the nth root of that product. So what this means is if we're multiplying two radicals that have the same index here, and in this case 4, what we can do is go ahead and multiply everything under them and then take that entire product under that same radical. So what I mean is, since we're multiplying two fourth roots together, we're going to put this product under a fourth root. So we're going to take 3y squared times 6yz. So we're essentially combining these guys. Now what we want to do is go ahead and simplify everything under our radical. So 3y squared times 6yz, that's going to give us an 18y cubed times z. And we can't simplify that any further, so this would be our final answer. Okay, and this entire thing is under that fourth root. All right, let's look at this next example. This one is similar, but instead we're looking at the quotient rule for radicals. Now it says that the nth root of a quotient is going to be the quotient of the nth roots. So essentially, looking at this example here, this fifth root of this quotient is going to be applied to the numerator and the denominator separately. So what I mean is, this is going to be equivalent to taking the fifth root of 32 over the fifth root of y raised to the 20th power. Okay, so that would be our quotient rule here. And what we want to do then is simplify this. So 32, or the fifth root of 32 is going to be 2, since 2 raised to the fifth power is 32. And then for the denominator here, what we're going to do is we're going to use our exponent rules. Let's rewrite this radical as an exponent. This is going to be y raised to the 20 divided by 5 power. This is going to end up being 2 over y raised to the fourth power. And we can't simplify that any further, so this would be our final answer. Now for this next question here, question 74, we're going to simplify this radical in a slightly different way. If you haven't already done so, please make sure you look at the conditions for a simplified radical in the textbook. But for this one, we're primarily focused on the first condition, and that's that the radicand has no factor raised to a power greater than or equal to the index. So, for example, if we look at this one, we're taking the square root of this whole thing, and right off the bat, you can already tell that the square root of 169 is 13. So this tells me that this is not fully simplified. It doesn't satisfy that condition I just mentioned. So what we're going to do is use the product rule kind of in reverse, like we saw in the first example, to simplify each one of these. So what I mean is, this can be rewritten as the square root of 169 times the square root of s raised to the fifth power times the square root of t raised to the 10th power. Okay, so that's using our product rule in the opposite direction. And now we want to see if we can simplify each one of these. We already know that the square root of 169 is 13. So that's fairly simple here. Now looking at these next two guys, we want to make sure that we don't have a factor raised to a power greater than our index in this case, which is 2. So what I'm going to do is I'm going to try to rewrite these guys as perfect squares if possible, where their exponents are perfect squares, and try to simplify them as much as possible. What I mean is, this first one here with the square root of s raised to the fifth power, this is the same thing as s raised to the fourth power times s. And this 4 here is a nice number. This is going to simplify nicely with the square root. Similarly, for this next one here, I can rewrite this guy as the square root of t raised to the fifth power squared. Using our exponent rules here, this is the same thing as t raised to the 10th power. All right, so we're gonna use a couple different rules here. We still have this 13 here. Now for this next one, this simplifies again using my product rule as the square root of s raised to the 4th power times the square root of s. Now this one actually simplifies nicely right away. Remember the rule that we saw in section 7.1 here. If we have nth roots raised to the same nth power, these guys are going to cancel. We're just going to be left with what's underneath this radical here. So this square root and this 2 here cancels. So we're just left with t raised to the 5th power. And we can also see that, write this on the side here, because this is going to be the same thing as t raised to the 5th power squared raised to the 1/2 power because of this square root here. So this square and this 1/2 cancels, and we're just left with this t raised to the 5th power. Similarly here, this guy, the square root of s raised to the 4th power, is going to simplify into s squared. We still have the square root of s, and then we have this t raised to the 5th power. Now, just to keep track of everything, this s raised to the 4th power, or the square root of it, simplified because this is the same thing as s raised to the 4th power raised to the 1/2 power, which is the same thing as s raised to the 4th power divided by 2, which gives us s squared. So that's how we simplified that guy. And then lastly, let's rewrite this entire thing so that our radical comes last. So we're going to have 13s squared times t to the 5th power times the square root of s. That's generally just how we write our radical expressions once they're fully simplified, with our radical last attached to everything else. Now for this next one here, 111, what we want to do is multiply these two radical expressions. But remember, our product rule says that we can only multiply these guys if they have the same index. That's what we saw in this one and this one here. But the index of this one is 3 and the index of this one is 2. This is the same thing as, let's actually write it down here so we have more room. 4 raised to the 1/3 power times 3 raised to the 1/2 power. So we can't quite multiply them yet. What we actually need to do is rewrite them so that they have the same index. What we're going to do is look at both of the indexes here, 3 and 2, and find the least common multiple. Or essentially what we're trying to do is get a common denominator between these two. So in that case, our least common denominator or our least common multiple here is going to be 6. So what we're going to do is we're going to multiply the top and bottom of our rational exponents by something so that the denominator is 6. So for this first one here, we're going to multiply the top and bottom by 2. We're going to end up with 4 raised to the 2/6 power. And then for the second one, we're going to multiply the top and bottom by 3. So we get that 6 there. This is going to be 3 raised to the 3/6 power. So this is going to be the same thing as rewriting this as a radical expression here. This is going to be the 6th root of 4 squared times the 6th root of 3 cubed, right? This is going to give us, I'm running out of room here. We're going to take the 6th root of 4 squared, so that's going to be the 6th root of 16 times the 6th root of 3 cubed, which is going to be the 6th root of 27. So we're going to go ahead and multiply these guys together. Now they have the same index. So 16 times 27 is going to give us 432. So this simplifies to the 6th root of 432. And that's going to be our final answer. All right, so for the next two problems, we're going to be using formulas from our textbook. So again, check that out. For this first one here, we want to find the length of the unknown side of this right triangle. Now, since we're dealing with a right triangle here, we can use the Pythagorean theorem. It says that the square of one side of the triangle, which we call A, plus the square of the other side of the triangle, which we call B, is going to be equal to the hypotenuse of our triangle squared, which is C. So in other words, we can think of this as A, B, and C. Okay, so this is going to be our standard Pythagorean theorem. What we want to do is find the length of the unknown side B here. So we have our A and our C. So what we're going to do is plug in this value for B. We're going to have, or sorry, plug in our values for A and C. We're going to have 6 squared plus our unknown B squared is equal to our C squared, which was 9 squared. This is going to give us 36 plus b squared is equal to 81. And we're going to go ahead and solve for b. We're going to end up with, we're going to subtract 36 on both sides of our equation here. This is going to give us b squared is equal to 45. And then lastly, to solve for b, what we're going to do is take the square root of both sides to get rid of that square on b. We're going to end up with b is equal to the square root of 45. Now, this isn't going to be fully simplified yet, though, by the same reasoning that we saw in problem 74. What we're going to do is simplify this radical. So we have the square root of 45. This is going to be the same thing as the square root of 9 times 5, which is the same thing as the square root of 9 times the square root of 5. Oh, we know that the square root of 9 is going to give us 3. So our final fully simplified answer here for b is going to be that b is equal to 3 times the square root of 5. So that'll be this unknown side here on this right triangle. All right. I said that question 20 or 128 also involves a formula, and it's going to be the distance formula. So the distance between 2 points, which we'll call x sub 1, y sub 1, and x sub 2, y sub 2 for our 1 and 2 points here. So the distance between these guys is going to be the square root of, we're going to take our first or our second x coordinate and subtract out our first and then square it, and then add that to the difference between our two y coordinates and square it. We're going to take the square root of this entire thing. So that's going to be her distance formula. So if we want to find the distance between these two given points here, the first thing that I'm going to do is label these. So it doesn't matter in which order that you label them, but it does matter in which order that you plug them into your equation. Okay? So I'm going to call this is going to be, let's call this one x sub 1 and y sub 1, and x sub 2 and y sub 2. Again, it doesn't matter in which way that you label it. This might just be a little bit easier because we have this negative here, so I wouldn't have to subtract a negative. Okay, so we're going to take -1 minus our x sub 1, which is going to be 5, and square it. Then we're going to add this to y sub 2, which is 2 minus y sub 1, which is 3, and square that. And again, this is all under our square root. Oh, all right, so let's go ahead and keep simplifying this. We're going to end up with -6 squared for our first term, plus -1 squared for our second. So this is going to give us 36 plus 1 here. This is going to be the square root of 37. And we can't simplify this any further, so this is our final answer. This is going to be the distance between our two given points in our problem. All right, and for our last problem in this video here, we want to find the equation of a circle given this center and this radius, and then graph this circle. So we're going to have another formula from our textbook, and this is the equation of a circle in center radius form. So it looks like this here: x minus h squared plus y minus k squared is equal to our radius squared. Now this is derived from our distance formula. So if you're curious, go ahead and check that out. But this h comma k here is going to be the center of our circle. Okay, so what we need to do then is just plug in our given information into the standard formula. We know the center of our circle is going to be -4 comma 3, so we're going to go ahead and plug that into our h and our k. So we're going to have x minus our h, and our h is a -4, so we have to be careful with signs here, plus y minus our k, which is a +3, is equal to our radius squared. Well, our radius is 2, so 2 squared. All right. Let's simplify this further. This is going to end up being x plus 4 squared plus y minus 3 squared is equal to 4. All right, so this is our equation of our circle, and then we're going to go ahead and graph it. So, like we said, our center is -4 comma 3, so we're going to go ahead and plot that on our graph. So -4 comma 3, that is going to be the center of our circle. Okay. Now, our radius is going to be 2 in this case, so what we're going to do is just move 2 units in every direction from the center. So that'll be another point, that'll be another point, that'll be another point, and that will be another point. So we'll go ahead and graph this circle. It'll look like this here. All right, so that is a rough sketch of a circle with center -4, 3 and radius 2.